subscribe button, and you also hit the notification button. Support this channel. To subscribe does not cost you a thing. It is free of charge. Thank you. So in this lesson, we are going to focus on Newton's second law. Newton's second law. Of course, we are going to look at all the laws of Newton's, but the main focus will be on the Newton's second law, which some people call it a problematic topic for most of the learners. But what I guarantee you is that by the end of this lesson, you should be able to state Newton's second law, Newton's first law, Newton's third law. You should be able to understand what we mean by net force. You should be able to make a calculation that have got two objects. You should be able to draw a free body diagram. You should be able to understand the components of gravitational force, and you should be able to calculate the kinetic friction, static friction, and their coefficients. So, ladies and gentlemen, we may start. For lesson number 1 of work, energy, and power, when I introduced it, I touched on Newton's second law. I tried to explain the work, energy, and power in terms of Newton's second law because I explained the components of the gravitational force, and I explained the free body diagram. In this lesson, let me start from a free body diagram. The free body diagram, we can start by talking about normal force. Normal force. We can start by talking about normal force. We use the word F, N as a subscript to represent the normal force. What is normal force? What is the normal force? We say that normal force is a force that the surface exerts on an object it is in contact with, and it acts perpendicular to the surface. So what is the normal force? Normal force is a force that the surface of an object exerts on an object it is in contact with, and it acts perpendicular to the surface. Normal force is a force that the surface exerts to an object it is in contact with, and it acts perpendicular to an object. It acts perpendicular to the surface of an object. The reason I'm starting with normal force is to make you understand these forces, because I assume that I'm teaching people who were taught before. If you were not taught before, I also guarantee you that you'll be catered for and you will understand what we'll be doing. Ladies and gentlemen, my name is Mr. Bila, and I work at Madam Nele Central Circuit. I'm a teacher by profession. I'm also venturing into assisting kids on YouTube because that's where our 2000 kids are. I'm a 2K, so I'm coming here, my 2K, to assist you. Normal force is a force that the surface exerts on an object. What do we mean by a surface? When we talk about the surface, we are talking about the place where an object is. that support. You see where I am walking. I'm walking on the surface. So when we talk about the surface, we are talking about where I am standing. You understand? So the surface of this object, it is this paper. Can you see? This paper is laying on the surface. So that's what we mean by the surface. So a normal force is a force which a surface exerts on an object that it is in contact with. So this surface, which is a paper, this surface is going to exert a force on this object. So it means whenever you put something on the surface is going to do what? To exert the force. And obvious, since the surface is below the object, when it exerts the force will go up because it is the surface that is exerting the force to the object. You understand? So that's what we mean by the surface. It means I'm walking on the floor now. This floor is exerting a force on me because I am in contact with it. And this force, it is always perpendicular to that surface. The force is always perpendicular. So what do we mean by this word perpendicular? You know that in maths we use I can say a T which is upside down. We use this symbol of a T which is upside down to represent perpendicular. When we talk about perpendicular, we are talking about an angle of 90 degrees, meeting at an angle of 90 degrees. Just like the corner of a goalpost, just like the corner of this question paper. I'm holding a question paper here, I'm holding a paper rather. You see this corner, this corner is 90 degrees. This corner is 90 degrees. Can you see the corner? I'll shade it so that you can see. The corner that is here, it is 90 degrees. The corner that is here, it is 90 degrees. So it means that this line is perpendicular to this one. So what do we mean? It means the normal force is going to create a corner like this to the surface. So whenever we draw the normal force, we should have a 90 degrees. Whenever we draw a normal force, we should have what? A 90 degrees. So a normal force is a force which the surface exerts to an object it is in contact with, and it acts perpendicular to the surface, meaning that the surface and the normal force should always be forming 90 degrees because they are perpendicular. Okay, so we have started. I've explained what we mean by normal force as my way to introduce this topic. Then we are going to talk about frictional force, which will represent by Fk or Ff. Some write Ff. So I'm going to write both of them. Fk it represents kinetic friction, and Ff still represent the kinetic friction. What do we mean by kinetic friction? You see, as I'm moving this side, I'm experiencing friction. But that friction that I'm experiencing does not cause me to stop. Understand? So kinetic friction is when you're experiencing friction while you are moving. It's friction on a moving object. Just like the car. If the car is rolling, the wheels of the car are rolling, the car will be experiencing friction as it moves. So that's why it is called kinetic friction, because remember, kinetic, it talks about movement. So we use Fk and Ff to represent friction. We know that friction is a force that opposes the motion of an object, and it acts parallel to an object. You know that friction opposes the motion of an object and it acts parallel to an object. It means that if my motion is this side, if I'm going this side, friction will be going that other side. If I'm going this side, friction will be going that other side, because friction is a force that opposes the motion of an object and act parallel to a motion of an object. It acts parallel. Okay, so we're also going to have gravitational force, which will represent by Fg. Gravitational force. We represent gravitational force by Fg. I've already said that this is frictional force, which will represent by Fk, and Ff. Gravitational force will represent by Fg. Okay, we're also going to have applied force. We're going to have applied force. Applied force is the force that causes an object to move, to be displaced. That is the applied force. If ever you see this thing is moving because I'm applying a force on it. It cannot move on itself. So it is moving because I'm applying a force on it. This is a surface. Can you see this? This object is just lying on the surface. Then I push it. When I push it, we say that I'm applying a force. When I push this object and it moves, we say that I'm applying a force. So we use Fa to represent the applied force. We use Fa to represent applied force. So applied force is the force that will be acting on an object and causing an object to move. As the example that I'm giving, that when I push this object and it moves like that, we say that I'm applying a force. So that's what we mean by the applied force, which we represent by Fa. We are going to have another form of applied force. When I apply a force on a string, or a rope, we call that applied force a special type of applied force, and we call that applied force. We call it a tension. So let's say this is an object, right? Then here there is a string or there is a rope. So I start to pull this string. As I'm pulling it, I'm applying a force, can you see? But since the force is on a string like this, we say that applied force is called the tension. So tension is a form of applied force which is being applied on a string or a rope. You understand? So we're going to have Ft. Ft represents tension force. So we represent tension force by writing Ft. So applied force and tension, it is the same thing. It is just that when we're applying a force on a string or on a rope, we call it the tension. Okay, I've explained these forces. To get more details about this, check lesson number 1 for work, energy, and power. I've given a very good introduction because now my focus is not work, energy, and power, is to explain Newton's second law, which is giving problem to many kids. Let me start by free body diagram. Through my process of teaching kids in different places, I realized that many kids cannot be able to draw a free body diagram. Most of them, they do not follow the prescribed rules when it comes to drawing free body diagrams. And kids do not practice to draw a free body diagram because they assume that they know. And free body diagram, they've got a lot of marks. You find that kids loses a lot of marks. We find free body diagram in 3 topics. We find them in vertical projectile. We find free body diagram in this topic of Newton's second law, work, energy, and power. So you can find that a free body diagram have got around 10 marks or 12 marks in a question paper for paper 1. So please, give yourself time, get a question paper, drawing free body diagram only, and check if you understand, because I realize that many kids do not know how to draw a free body diagram. They just draw few forces correctly. Obviously, it is the gravitational force. But when it comes to other forces, normal forces, when you give them objects on an incline or objects that are moving vertical, learners tend to fail to draw a free body diagram for that. Okay? So now let us draw a free body diagram. The rule that I'm going to tell you now, it is only one rule. Right? That rule is that the arrow is not allowed. The arrow is not allowed to point the body. The arrow is not allowed to point a body. What do you mean? If this is the body which is represented by a dot, you are not allowed to draw something like this and it points the body. The arrow is not allowed to point at a body. We are not allowed in a free body diagram to point at a body. So this is the first rule, the rule that I must tell you. The second one is that normal force is perpendicular to the surface. The normal force is perpendicular to the surface all the time. What do we mean by perpendicular? It means if this is the surface, normal force is going to point up like that. Then it is going to create a 90 degrees. If it is the surface is like this, it means normal force needs to point up like that. Why is it pointing up like this? So that we can have a 90 degrees. We know that normal force is always pointing up, but it does not mean that we need to forget that normal force is perpendicular to the surface. We can't draw it like this and say normal force is pointing up. What about this angle? This angle is not 90 degrees, and normal force must be 90 degrees with the surface. It is perpendicular to the surface. So that is the second rule that we can touch on now. Then we can start to draw a free body diagram. When we draw a free body diagram, I advise that do not draw the components of forces. Do not draw components of forces. Rather, draw the forces themselves, not the components. Okay? Let us start. Let's say we have an object, 3 kg, which is on a rough surface. The surface is rough. The surface is rough. The object is pulled. The object is being pulled to the right. The object is moving on the rough surface. The object there's a force that is applied. Force F is applied to move an object to the right. You can see that the object is going that side. How do we draw a free body diagram for this one? We just going to draw a body by drawing a dot. Gravitational force is a line which is always pointing down. The line is a vertical. So to represent gravitational force, we just draw a line which is vertically pointing down. And I've just showed you that we use FG to represent gravitational force. Then, for normal force, you draw a line which is pointing up. A line which is pointing up, just like that. Then, apply force, draw FA. You draw a line which is pointing where this F is pointing. Can you see? You can write FA or F if you are told that this is force F. Then there is friction. Then you draw FK or you write FF, which represents the frictional force. You understand, right? So this is how we draw a free body diagram for this one. This is the simplest free body diagram, but we do have complicated free body diagram. Let me show you. Okay. We still have the same 3 kg. We still have the same 3 kg. Look at it. It is moving on a rough surface. It is connected with a 6 kg. It is connected to a 6 kg box. Both of them are moving on the rough surface, as you can see. Then there is force F, which is acting on the 6 kg to pull the whole system. Both of them are moving on the rough surface. So there is a string, you can see this is a string. This is a string which is attaching the two boxes. We must draw a free body diagram of the 6 kg. I want us to draw a free body diagram for the 6 kg. When we draw a free body diagram, we are going to draw a body by drawing a dot. We draw a very nice dot, then we draw a line which is pointing down, vertically down. And we call it Fg, that is the gravitational force. We draw another line which is normal force. Then the surface, the forces which are moving with the surface. Look, then we have the applied force which is moving this side. We are told that we have a rough surface. Rough surface, it tells us about the friction. Rather, let me just, for those who may not find a chance to go and watch lesson 1 of work, energy and power. When you hear the word rough surface, it means friction. Rough surface, it means friction. Smooth surface, it means no friction. Rough surface, it means there is friction. Smooth surface, it means that there is no friction. So you need to take note of the two words. Smooth surface and rough surface. You need to take note of that. Okay. Then we were still here. The applied force, the gravitational force. Then on this object there is friction. Can you see? Then we're going to have frictional force. We're going to have what? The frictional force. But don't we have tension? Yes, we do have tension. So we need to represent tension. We just draw another line. We just extend it. Just extend it like that, and we have Ft. Do you see that? Because tension is parallel to the surface. You see these forces, they are parallel. Notice that I'm not drawing a line and I'm drawing two arrows. No, let us avoid that. Draw two lines. Each force should stand on its own. You must not have a force at the top of another force. Can you see? Both of them are parallel to an object. I didn't draw Ft at the top of this one. So when you draw two forces together, you draw them like this. You draw the first line, you draw the second line. You can make the body, which is the dot, to be much more bigger. Isn't it the object is going that side because the applied force is pointing that side? Then friction is opposing the motion of an object. Then tension, this 3 kg is pulling the string back. So the tension is pointing this side to the left, backwards. So that's how we represent. We are not done yet by complicated free body diagrams. These free body diagrams, they assist a lot when we start to deal with Newton's second law. When we start to use that formula of F net is equals to ma. Free body diagram will assist us a lot because the word F net have got a meaning. the word net force has got a meaning. It means all the forces which are acting on an object. But I will explain in details when we get there. Let's say we have an object. Here is an object. Here is an object like that. It's on a rough surface. The surface is rough. I've already told you that the word rough surface, it means that there is friction. The word rough surface, it means there is friction. Then there is force. Force F, you can see where the force is pointing. The force is pointing that side. I can say there's a string which you have attached. 10 kg attached to 2 kg. 10 kg is attached to 2 kg by a string. You can see the string, and this string is a rope. I told you it's applied force on a rope. It's called a tension. Force F, which is the applied force, can you see? It is pointing downward, sort of. It is pointing downward. You can see this is the arrow. So this object is going that side. The system is going that side because of how this force is pointing. Someone can ask, how is this possible? It is very possible, and you do it every day. When you are pushing a trolley, how do you push a trolley? You bend your hands like this, then the trolley will move in that direction, understand? So when you are pushing a trolley, you bend your hands like this, and you start to move. And your force is being applied downwards. The same applied to this. That is what is happening. So this is very possible. So how do we represent a free body diagram for this 10 kg? Remember, one of the rules that I gave you for drawing a free body diagram is that you are not allowed to point at the body. The arrow is not allowed to point at the body. The arrow is not allowed to point at the body. So the manner in which you do it, is that by drawing a free body diagram for 10 kg, you are going to have a dot. You are going to have a dot which represents the box, the 10 kg box. Then we have the gravitational force. I told you the gravitational force all the time, whether it's on an incline or a flat surface, you just draw a line which is vertically pointing down, and you just write Fg. Then the normal force is the force that the surface exerts on an object it is in contact with. So the normal force is going to be Fn. And you see, then we are told that there is friction. So it means the friction is opposing the motion, Fk. Because the object is going that side, it means friction is going that side. What about tension? This 2 kg object is causing this rope to be pulled backward, meaning that tension and friction are pointing at the same direction. So we're going to have tension, Ft. Remember that these things are not drawn up to scale, meaning that the length of the lines do not matter. It is not drawn up to scale. Then, now, we need to represent this force. The question now is, where is this force pointing? Remember, we are not allowed to draw something that is going to come and point here. We are not allowed to point at the body. But we need to show that where does this force push this object to? In which direction does this force push this object to? It means this force is pushing the object downwards. So it means the force is going down. So it means we're going to draw that force just like this. Apply force. Because, what am I writing? Fa. I must write Fa, not Fn. So this force is pulling the 10 kg down. It means the force is going to pass through and it moves here. So that's why we represent it like this. We cannot draw it here because we're not allowed to point at the body. So that's how we represent a free body diagram for this one. Understand? Then we can talk about the incline. Then we're going to the Newton's second law. We talk about it into details. Let us talk about the free body diagram of an object on an incline. An object on an incline. Let us talk about an object on an incline. Let's take here we have a 30 degrees, then we have got an object, a 4 kg on a rough surface. We have got a 4 kg on a rough surface. This object is going down, so there is a force which is pulling it down, force F. Understand? So how do we represent this? How do we represent this using a free body diagram? You can see there is force F which is pulling the object down on a rough surface. So what we're going to do, what you need to notice is that this object is moving down because there's a force that is applied. But it does not mean that all the time when an object is moving down, there is a force that is applied. An object can be released. To release is to let it go here. Then when you let go, the object will move on its own. So sometimes it's possible that an object can move down without having any force which was applied. So you need to take note of that. So to draw a free body diagram of this one, I'm just going to draw the surface. Remember, where is the surface? These things are not going to be straight because this time around the surface is bended. It means we're going to have frictional force which is moving like this because the surface is also like that. You understand? Imagine a car which is moving here. If there is a car that is moving here, it means if the car is going this side, friction will be going sort of upwards. You understand? So if we want to represent this, we just draw a straight line like that. Then we make a what? We draw a body somewhere. This will give us a simpler way not to make mistakes. Then the force which is going down is force applied. Then frictional force is going to pull up. Understand? Then gravitational force, I told you, just draw a vertical line which is pointing down. A line which is pointing down. F, G. Then we come to normal force. I told you that a normal force is a force which is perpendicular to the object. Normal force is a force which is perpendicular to the surface of an object. So it means that we must make sure that here we have a perpendicular line, and then we have normal force. Why did I have to draw this line to point at this direction? So that here I can have a 90 degrees. If I were to draw a straight line like this, I was not going to have a 90 degrees here. Can you see this is not 90? So if I want to have a 90 degrees, I must draw what? The normal force to point at that other direction. Understand? So this is how we draw a free body diagram for an object on an incline. Okay. So let us go to scene 2. If you want more details about the free body diagram, please check lesson number 1 of Work, Energy and Power. Leave a comment. Search me on Facebook. I am Tommy Bilo on Facebook. I'm also Tommy Bilo on TikTok. Then you send me a message. I will make sure that I reach out to you and I explain, because that is my passion. Don't forget, subscribe to our channel. When you subscribe, it does not cost you a thing. So kindly please subscribe. Thank you. Okay, let us continue with what we are doing. Let us move forward with what we are doing. Okay. Ladies and gentlemen, I want us to focus on calculating the kinetic friction. It is one of the things that gives our learners a problem. I want us to talk about kinetic friction. Kinetic friction, let me write. Kinetic friction. How do you calculate kinetic friction? Scenarios may differ, and some of the scenarios may be easier, but we're going to tackle all of them, simple and complex. When an object is on an incline, when an object is on a flat surface, and you name it. Ladies and gentlemen, kinetic friction formula is represented by kinetic friction is equal to N multiplied by UK. So this one stands for frictional force. Frictional force. Then N, I used to think that N stands for Newton. No, N does not stand for Newton. N stands for normal force. This N that you see here, it stands for normal force. The N that you see here, it stands for normal force. Then when it comes to UK, this is the coefficient of kinetic friction. As this is the kinetic friction, so this is the coefficient of kinetic friction. N stands for normal force. So one of the challenges that learners are faced with is the issue of how to calculate normal force, because there is no formula which we use to calculate the normal force. So let us start to deal with the issue of normal force. Okay, so I repeat, the N stands for normal force, not Newton, stands for normal force. Let's say we have an object which is lying on the surface. Can you see 2 kg? We have got a 2 kg object which is lying on a flat surface. When we want to represent the free body diagram of this object, normal force and gravitational force, we're going to draw a body which is a dot, then we draw a straight line. We draw a what? A straight line. Then this straight line we're going to have normal force pointing up, and we're going to have gravitational force pointing down. Can you see that? We have the normal force. So the normal force and the gravitational force. This is the free body diagram for this 2 kg. So you can see that gravitational force is equal to normal force. Gravitational force is equal to normal force. So gravitational force and normal force, both of them, they are equal. They are equal. So what does that mean? There is no formula to calculate the normal force. So in this scenario, we can talk about forces that are acting vertical. So to calculate normal force, we focus on the forces that are acting vertical upwards and downwards. So in this scenario, we have only two forces, normal force and gravitational force. And normal force is equal to gravitational force in this scenario. So it means Normal force, this end is equals to gravitational force. And the formula of the gravitational force is the weight. Weight is equals to mg. Mass multiplied by the gravitational acceleration, which is a constant, which is 9.8. So when we have an object which is lying flat on the surface, and the only forces which are acting upwards is gravitational force and normal force, it means normal force is equals to the gravitational force. It means the normal force is equals to the gravitational force. You understand? So it means the normal force for this one is equals to what? Normal force is equals to 2 multiplied by 9.8. Then normal force will give us the answer, which will multiply 2 times 9.8 multiplied by 2, which will give us 19. So the normal force is 19.6 Newton up. So it means if we want to calculate the kinetic friction, we're just going to come multiply the coefficient of kinetic friction, which they usually give us. Then we substitute the normal force, then we get the kinetic friction. So for scenarios whereby we have an object which is lying on the surface like this, to calculate the normal force, just calculate the gravitational force, and it is simple like that. Because with the normal force, because it's a force that is vertical, we check all the forces that are acting vertical, and we get to the answer. Ladies and gentlemen, I want us to touch something which is very important, and it's called the components. I want to touch the components, then I come back to the kinetic friction, because in this subsection I'm teaching you kinetic friction, then we'll go to the other stuff. Let's say we have force, applied force, which is like this, which is upward, and it is acting at 20 degrees. Can you see? We've got 40 Newton. We've got the 40 Newton, which is acting on this 6 kg. The surface is flat. Can you see that the applied force is acting at an angle of 20 degrees to the what? To the surface. Can you see that? So it means that this applied force can be broken into what we call the components. This applied force can be broken into what we call the components of the applied force. I can liken that to this. When we have a Cartesian plane, y and x, then we've got a radius. We usually call it radius. Then we've got the line which is like this. Usually come across this on trigonometry. Yeah. So that's what we have here. We find that this is force F, which is 40 Newton. Can you see? So this 40 Newton, it can be resolved into two components. The first component is what we call the x component, the x-axis. Can you see this? This is the x component. And the second component, it is the y component, the y-axis. So that's what I can explain. That's how I can explain to you. We can use this 40 Newton and we resolve it into two components. You don't have to be confused because these methods of components, they are coming from vectors. And since they are coming from vectors, we won't dwell much into vectors. We will just show you how to get the component of a force, because when the force is like this, I told you that to calculate the normal force, we need all the forces that are acting vertically upwards. We need the forces that are acting vertically upwards and downwards. As long as that force is acting vertically, we are interested in those kind of forces. You understand? Okay. So we are able to resolve this 40 Newton into components, the horizontal component and the vertical component. So let us resolve it. When you want to resolve a force into the horizontal component, which is on the x-axis, you say Fx is equals to that force, which is this force, multiplied by what? Cos theta. We are using cos because it's the forces which is on the x-axis, while resolving it on the x-axis, and theta, it is the angle at which that force is to the surface. It's the angle between the force and the surface. And the angle between the force and the surface is what? Is 20 degrees in this scenario. So it means if we want to resolve this 40, we can resolve it as Fx is equals to 40 cos 20. So the x component of that force is going to be 40 multiplied by cos 20, which will give us 37,59. 37,59 Newton. So it means that the x component, the horizontal component of this 40 Newton is what? 37,59. Then what about the vertical component, which is the what? Fy. The vertical component, I told you that we say force multiplied by the sine, force multiplied by sine theta. Why sine? Because now we're focusing on the vertical part, the y-axis. You understand? So it means the y component for that one is going to be Fy, which is going to be 40 sine 20. So Fy there is going to be 40 multiplied by sine 20, which will give us 40 multiplied by sine 20, which will give us 13,68. That is 13,68. It means that the vertical component of that force is what? Is 13,68. The vertical component is 13,68. So that's how we resolve forces into different components. But we are resolving which forces? We are resolving the applied force when it occurs on a particular angle. A force is applied at a particular angle, like when you are pushing a trolley. You are applying a force, but your force is at a particular angle. So we can resolve your force into two components, the horizontal component and the vertical component. Okay, so this is very important. It's very important for us to be able to understand how we resolve into component. Then, since I've showed you to resolve into component, I can just recap with you. To resolve into horizontal component, you just say Fx is equal to F cos theta. To resolve into vertical component, you just say Fy is equal to force multiplied by sine theta. Then you get the two components. So this force is going to have two components, the horizontal component and the vertical component, which is something that it is very important that we check. So that's how we resolve our forces into two components. Okay, so now I want us to go back to normal force since I've touched the issues of component. You don't have to close your mind a lot. It's just a component. Whenever you see a force which is not horizontal and which is not vertical, that force it can be resolved into what? Into component. But when a force is vertical, it can never be resolved into component, just like that. So look at this one. It's the same scenario as the one, not changing a scenario. I want us to calculate the normal force. Here is the force, and this force is acting at 20 degrees, and that is 40 Newton. 40 Newton. I want us to calculate the what? The normal force for this scenario. Let us calculate the normal force for what? For this scenario. How do we calculate the normal force for this scenario? We check how many forces do we have which are acting vertical. Forces that are vertical in this scenario. How many of them? First, we are going to have normal force. The second one is gravitational force. The third one is Fy. Because I just told you that this force, it can be resolved into components. So this force can be resolved into components. So we have got three forces which are acting what? Vertical. So when we calculate the normal force, we focus on the forces that are acting vertical. When we calculate the normal force, we focus on forces that are acting vertical. Okay, so now let us see what do we do. So for this case, in this case, how do we solve it? What is the direction of the gravitational force for this one? Isn't it we say gravitational force, the Fx, the Fy component, and the normal force? What is the direction of the gravitational force? The gravitational force is going to point down. Right? The gravitational force is going to do what? To point down. Then, what about the Fy? Will it point down or will it point up? Fy is going to point up. Why is Fy pointing up? Fy is being influenced by its force. Fy is being influenced by F, because this is force F. So force F is pointing up. It means even Fy will point up. If force F was pointing down, it means even Fy will be pointing down. You understand? So since force F or 40 Newton is pointing up, it means Fy is going to point up also. Its component, its horizontal, vertical component is going to point up because it is also pointing up. You understand? So if we resolve a force that is pointing up, we resolve it into a vertical component, it will also point up. You understand? So we have got these forces, which are acting upwards. You understand? So it means that normal force, you know that vectors, if one vector is going up and the other is going down, it means the vectors are going to do what? To cancel. So it means the normal force is equals to, right? Normal force is equals to gravitational force minus Fy. Normal force is equals to gravitational force minus Fy. So that's how we calculate. So it means for this scenario, we're going to have normal force which is equals to mg minus F sine theta. Normal force which would be, why are we writing minus here? It is because the force is going up, its component will go up. Gravitational force is always downward, so they are moving in different direction. When we calculate normal force, we focus on forces that are upwards only. So it means normal force here is going to be 6 multiplied by 9,8 minus 40 sine 20. Meaning that our normal force is going to be 6 multiplied by 9,8 minus 40 sine 20. And then that will give us 45,12 newtons. So that is our normal force. So the problem comes when we are faced with a situation where we need to calculate the what? The normal force. So I showed you how we calculate the normal force. Okay. Let me give you another scenario whereby we need to calculate the what? The normal force. Let me give you the second scenario of calculating the normal force. Let me give you the second scenario of calculating the normal force. So this is how we calculate the normal force. For this scenario, let's say we have got an object and there is force F which is pointing down, and this force is what? 60 Newton. We have got 60 Newton force F which is pointing down. It is acting at an angle of 30 degrees. Can you see that? How do you calculate normal force for this one? How many forces are acting vertically? The forces that are acting vertically is normal force. The second one is gravitational force. The third one is F. Let us call this one Y. F-A-Y. It means the forces which are acting vertical is the vertical component of this applied force of 60 Newton. I told you that if the force is going down, its component will go down. So it means the component of this force will be going down. Understand? What about gravitational force? Gravitational force is always downward. So it means the vectors are moving in the same direction. It means Fy is downward, Fg is downward. Understand? So it means these two forces are moving down, going in the same direction. It means that vectors are going to add or sum each other. Understand? So it means the normal force for this one is going to be Fg plus Fay. That is the normal force. So normal force is going to be gravitational force, which is Mg. Here we're going to have F sine theta. Normal force is equals to, let's say I'm saying this one is 10 kg. Normal force is going to be 10 multiplied by 9,8 plus force, which is 60 sine 30. So then we get the normal force. Our normal force will become 10 multiplied by 9,8 plus 60 sine 8. Then we get 158. Normal force is 158 Newton. Understand? So that's how we calculate the what? The normal force. So at this stage, I just want to show you how we calculate the normal force to get the what? The kinetic friction. How we get normal force? How we calculate normal force to get the kinetic friction? In lesson number 2, I'll be showing you the application of the formula of F net is equals to ma. Understand? Okay. So let us talk about an object on an incline. an object on an incline. Object on an incline. When it comes to an object on an incline, let's say this is the incline. Then on that incline, this is what we have. It's 5 kg. So let us draw a few body diagrams for this one. Let me draw it here. I'm going to have a dot, then I have what? Fg. Then I have normal force, Fn. Then here I'm going to focus on these two forces because I want to show you the components of the gravitational force. Gravitational force is going to have two components. When an object is on an incline, the first component of the gravitational force will be pulling an object to come downwards in this direction. The other component will be pulling this object to move down in this direction. You understand? So we're going to have what we call the vertical component and the horizontal component. We're going to have two components. The FG perpendicular and FG parallel. There are horizontal, one is horizontal and the other is perpendicular. So let us look at it. So we are going to have a component of the gravitational force which will be continuous with the normal force, like that. It is just a continuation of the normal force, and this one will point downward, and it is called the gravitational force perpendicular. Why is it called perpendicular? Because it is perpendicular to the surface as it is continuous with the normal force. You know that a normal force is a force that surface exerts and it is perpendicular to the surface. You understand? So Fg perpendicular is going to be continuous with the normal force and it will be perpendicular. That's why it's called Fg perpendicular. Then the function of this force is to exert a force on an object that will cause this object to be pressed on an incline. You can see this is an incline. So this force will be pulling this object to stick even more to the incline so that the object does not move down. So the function of the Fg perpendicular is to pull this object downward on this direction, causing it to stick on the surface so that it does not flow down. That is the work of the Fg perpendicular. Then we have another force which is called Fg parallel. Fg parallel will be parallel to the surface. Will be what? Parallel to the surface. This is Fg. This is Fg. So these are components. Fg will be pointing downwards. Will be pointing downward. It is called Fg parallel. It is called Fg. You can see that there is a triangle that is created. So this one is called Fg parallel. It is parallel to the surface. What is its function? Its function is to stress an object to move down the incline. Fg parallel is to stress an object to move down the incline. So the function of Fg parallel is to stress an object to move down the incline. So as the object moves down the incline, what is going to happen? If the force of gravity is much more stronger than the Fg parallel, it means the object can move down by itself because it is being stressed to move down. As you can see that Fg parallel, it acts on an object in a manner that it must move down. So the FG parallel is downward, stressing an object to move down, stressing an object to move down. That's why if sometimes you will hear reports in the news that an object have moved down, I mean a car, not an object. A car have moved while the driver was not there and it collided with other cars. It is because when a car is pegged on an incline like this, the FG parallel will keep on acting on the car, stressing the car to move down. If the braking system of the car is not much more stronger, it can be overcome by the FG parallel. The car will end up moving down on its own, understand? So we have two types of forces, FG parallel and FG perpendicular. I've explained in lesson number 1 of work, energy and power into details, the FG parallel and FG perpendicular. So I'm linking the two lessons. So look at this. These forces, how do we calculate them? What is the formula? The FG parallel, when we calculate it, we say force. Remember, a component is just force, then we have trig ratio theta. That's how we move. Let's say here we have got 25. So it means that we're going to have mg, which is force. Then, since it's FG perpendicular, we're going to use sine theta. What you will notice is that there is a change. Remember that for perpendicular, for forces that are vertical up, we were using sine. For forces that are horizontal, we were using cos. But with this one, there are specialities, there are changes, and that is because the triangle have turned to the upside down. What do we mean by a triangle has turned to the upside down? You know the Cartesian plane for this one. The Cartesian plane is this. You see this line, and this line is a what? It's a Cartesian plane. If we can turn this to stand straight, we are going to have something like this. And this triangle is going to be somewhere here. So this is what we are going to have. This is what we are going to have. And with the first triangles, with the first scenarios, you saw I drew something like this at first, then. So, if we take this triangle, we take it, we rotate it to give us that form, or let me draw it here so that you can understand. You can see this triangle, how it is. If we rotate it and it forms something like this, cos will change into sine and sine will change into cos. I will demonstrate it to you shortly, but I've demonstrated it more on work, energy and power, lesson number 1. So the formula for FG perpendicular, vertical, it is going to be mg cos theta. Notice these changes. When it comes to gravitational force, the component of gravitational force, they use a trig ratio which is opposite to what we have been using in resolving the components of all those other forces. Okay, let me make a demonstration that why are we using sine here and this one is parallel? Why are we using cos for something that is vertical? Why for the other ones we were using parallel, we're using cos, vertical, we're using sine. What happened? What changed? Okay, let's say, gentlemen, let's say we've got the x, you know this side is called the x, right? Let's say here we've got 4, Then here we've got 3. This is our radius. This is 6. Can you see? That is our radius. That is 6. This is what we've been having, right? Remember, we're having an object which is like this with a force which can act either way at a particular angle. Then here I can say is theta. It's a particular angle. I want to show you why I'm using sine here and cos. What changed? Because this time around, since we're dealing with gravitational force for vertical, we're using cos. For horizontal, we're using sine. And something changed here. So why is that? Let me show you. From mathematics, we know that sine theta is equals to y over r. Isn't it? Cos theta is going to be s over r. We know these 3 ratios. So let us substitute numbers. Sine theta is equals to y over r. Which one is y? Y is 3. It means we're going to have 3 over 6. This one, cos theta is x over r. Which one is x? We're going to have 4 over 6. So that's what we have. So see what we are having here. As I was telling you that this Cartesian plane, we're going to put it straight, and when it is straight, this triangle is going to be like this. It's like we took this triangle and we rotated it like this. It was like this, right? Then we rotated it like this. So it means that this triangle, it is going to do what? It is going to be rotated, and it will come to another position. The very same triangle will come to what? Will come to another position. So it means if we happen to rotate this triangle, we are going to form what? It means that this one, it is going to change. We're going to have a triangle like this. If we rotate it right, we're going to have a triangle like that. Can you see what we have? It means that what we have as an x will become y. It means 3 will become our x. It means 3 will come here. Can you see? 3 will come here. What about 3 will come there? Then what about 4? 4 will become here. R will never change. Can you see that? R will never change. It's when we've shifted the triangle. Isn't it? The triangle was here, then the triangle was here. The very same triangle. So if we turn 3 will be horizontal this time around. Then 4 will be vertical. The R radius is not going to change. Can you see what we have here? So let us do the same thing. Since we've shifted the triangle, let us do the same thing. Sine theta is equal to y over r. Then cos theta is x over r. Let us see. Using this triangle, y, which one is y? Y is 4. It's 4 over 6. Using this one, what is x? X is 3 over 6. Let us check. Which one? Cos is 3 over 6 this side. 3 over 6 this side is sine. Can you see? When we compare. So it means if we have the way a triangle is positioned, if the triangle changes as it changed here, we're going to have cos becoming sine. Look at it. Sine is 3 over 6 this side when the triangle is like this. But what you can see here, there is a what? There is a change. You can see that there is a what? A change. Can you see that? So 3 over 6 is sine. 3 over 6 is cos this side. So there is a what? There is a difference. Can you see that? There is a difference. So